academic researcher, Sung Kyun Kwan, University, South Korea. We have Dr. Kare, Head Department of Chemistry. We have Mr. Kumavat, Assistant Professor, Department of Botany. We also have Mr. R.V. Gowde, Assistant Professor, Department of Chemistry. To begin with, I would like to request Dr. A. Kare to welcome once again Dr. Chaitanya Kanade by offering a flower as a token of appreciation and love. Please have a big round of applause. Thank you very much, sir. Now I would request Mr. R.V. Gowde to introduce our keynote speaker. Over to you, sir.
Good morning, one and all. First of all, I would like to hearty welcome in the Dft College, Mansur, at the occasion of this international seminar. I would like to express special welcome to Art, Commerce and Science College, Naranggaon students and their teachers. Now I am going to introduce a speaker of this session, Honorable Dr. Chaitanya Kanade sir. In the academic career of Kanade sir, did outstanding performance. He did BSc, MSc dual degree program in ISER Pune, and we know reputation of ISER Pune, which is located near to NCL. He did PhD from South Korea, Suncheon University, in the field of nanoscience. During his PhD work, he published 10 research papers in a well-reputed journal such as American Chemical Society and European Chemical Society. And all we know, the standard of that society or that work published in that journal is more creditable for a researcher. Now, today's speaker presently working as a research associate in the CMET Pune, and during his career development or academic career, he awarded by 3 different fellowships. In that, DST Inspire Fellowship Program, Brain Korean 24 Scholarship, International Student Scholarship. I think with this biodata, definitely our student motivate, and they also they will do something in research. And with this short introduction, I request guest of this session, please continue.
Thank you very much, sir, for introduction of today's keynote speaker. We also welcome Thackeray sir for Raman Mapping. And I would like to request our today's keynote speaker, Honorable Dr. Chaitanya Kanade sir from South Korea, to share his view, thought, and advice. Please, sir.
Students, please keep silence. Try to understand what sir wants to talk with you. Keep your questions ready so that after the session, we can discuss on it.
Am I audible? Okay. Okay, am I audible now? Yeah. So first of all, thank you for such a warm introduction, Professor. And I would like to thank Dr. Shinde sir, all the organizing committee members, and as well as all the students who are present here, who are like eager to know so much about the upgoing research in the scientific community. So first of all, I would like to thank Shinde sir also and the Dft College for giving me opportunity to share the stage with such a renowned and promising researchers such as Dr. Raman Mapping and as well as Dr. Kalyan Sundaram. So I hope you all let him know. So now I will start with my presentation. So basically, I will talk about the two-dimensional materials, which are considering to be the future materials for upcoming development in the energy devices or the technological devices or electronic devices. So basically, from all the fields, currently the research is going on the two-dimensional materials. So basically, I will here in this seminar, I will cover about the 2D materials, their introduction, their importance, as well as what are the different ways we can synthesize these materials. Along with this, how can we recognize the different properties using the well-known characterization technique, which the currently you all students are studying about, and how to characterize using those techniques. What are the information we can get from those techniques? I will let you know, and I will show you. And further, I will show the application part of these 2D materials, where exactly these 2D materials we can use, and how other researchers are using it. And finally, the importance of these 2D materials in current technological field. So to start, I will introduce about the 2D materials. So as you may know, there are different dimensions. So depending on the dimension you are talking about, such as 3D, 2D, 1D, or 0 dimensions, there are different types of materials. So currently there have been many decades the research is going on 3D materials, and from 3D to nano materials, and now eventually the people are working on the two-dimensional part of these materials. So along with that, there are 1D materials also. So basically, if you consider the carbon nanotube, which is the example of the one-dimensional, and the 0-dimensional materials are, as you may know, as you may have heard about the quantum materials or quantum dots. So these are the example of 0-dimensional materials, since their property get enhanced by restriction of their dimensions. So if you consider theoretically the Bohr's radius and the exciton's radius, so because of that, the emergence of these properties takes place. That's why as you restrict each dimension, you are getting different emergent properties in these materials. So as the research is going on in this field, the people are coming to study the lower and lower dimensions. But basically today I will mostly talk about the two-dimensional materials. And as you may guys all know, the most well-known two-dimensional material is graphene in scientific community. Since its discovery, the research is very fastly growing in that dimensions. But along with the graphene, there are other two-dimensional materials, which are such as hexagonal boron nitride, which is also known as HBN. Another one is MOS2 or the transition dimetal chalcogenides. Along with MOS2, there are WS2 or MOSC2, WSC2, or other other TMDC combination. So in upcoming part, I will more talking about this TMDC materials. And there are other well-known example of two-dimensional materials, black phosphorus. So these materials are also now used in the solar materials, which is the topic of our today's seminar. But as you may know, why there is need of other 2D materials since after the discovery of graphene. So basically, as you may know, the carbon is a conducting material. So it doesn't have any band gap, or it doesn't have any insulting properties. Or if we want to use it for heat isolation, we cannot specifically use since it is a conductivity and all. So that's why in different part of electronic or device management, we need a different property of materials. So that's why there are need of other 2D materials. Since we are going in the two-dimensional devices now, so other part of the devices also need to be in two-dimensional. That's why there is a need of these other 2D materials. So here the HBN is example of insulator. So HBN is considered to be an insulator. So that's why it mostly uses to enhance the property of other 2D materials as well as the heat management and other properties. Another example is MOS2 is considered to be a semiconducting material depending on its structure. So these semiconducting materials, like by using their band gap, they are useful for many other applications. For example, solar cells or the photosensor, photodetector, or sometimes their other conductivity part is also useful for the photocatalysis or other things, which I will be cover further. So as I talked before, these 2D materials, as we see the structure, you can here their band gap has been shown. You can see in case of HBN, the insulating nature of HBN can be seen, and considering the other black phosphorus or graphene, those are like conducting, and Pmdc is more about semiconducting material. So to talk more about Pmdc materials, so basically Pmdc is transition metal dichalcogenides. So in periodic table, if you take the transition metals and if you react with them, the chalcogenide family, then you can get the different types of transition metal dichalcogenides. So there are some examples such as tantalum sulfide, molybdenum sulfide, as well as neodymium, tungsten sulfide, as well as their selenide and tellurium parts. So these materials are important because these are layered materials, and they have, since these materials are 2D, they can be easily separated, easily synthesized using many techniques, and using their high surface area due to the 2D nature, also the self-standing nature, because even if you can synthesize two-dimensional, you need to be self-standing in order to use it for device purpose, or you need to transfer it in order to develop some technology or in order to fabricate other things. So these kind of properties of these Pmdc materials makes them interesting, and I think from last decade there have been many research going on in these fields. So how can we synthesize these 2D materials? I will cover now. So basically, since you guys are MSc, most of the students, so you guys may know about top-down method as well as the bottom-up approach. So basically, top-down is from like from bulk. We have to restrict the dimension. We have to go lower dimension or lower size, and then we will ultimately get the two-dimensional these materials. And most of the mechanical or physical methods are considered to be a top-down method, but not necessarily. And as well as there is bottom-up method, which is basically from element we will build up to whatever the size or desire we want. So mostly the chemical methods are used for bottom-up approaches, but which is also not necessary. So here I'm giving 2 examples. I will also give more examples further. So in mechanical exfoliation, which is the first technique was reported for the synthesis of graphene. So using by a simple scotch tape method, they separated the single layer graphene from the graphite. And then there are another methods such as chemical synthesis. So there are like organic synthesis as well as hydrothermal synthesis we can use in order to synthesize this sheet-like nature, and with very bulk, very large quantity. So depending on what synthesis technique we are using, there are some advantages and disadvantages. So if we consider the mechanical exfoliation, as I said before, using the scotch tape method or transfer method, it is easy to transfer, as well as we can highly selective the material. Suppose we want one kind of material on downwards, on top of which another material, we can easily do that. But another problem using this mechanical exfoliation, such as we cannot reproduce because the dimension of the 2D material we are lifting off is not controllable in this case. Also, the one device we can fabricate using such a techniques, but for industrial application we need multiple devices in very short time, or like in a single step. So another method, as I mentioned, is like hydrothermal or intercalation process, which basically is like large scale synthesis of these 2D materials. Like in this case, you can get multiple layers also in 2-dimensional, but a very large quantity. But another problem is in these chemical synthesis processes are mainly it requires sometimes multi-step, time consuming, and as well as since we are using some chemical reaction, there might be a chances of some impurity remain. So then we have to work on to remove these impurities also using these techniques. So people also use some another techniques such as electrochemical exfoliation, as you people may have learned about in your coursework. So basically by intercalation of lithium ion into the layered structures of these materials, you can separate them from each other, and then by using some ultrasonic energy, we can keep them in separate stages, as well as we can isolate them using some organic ligands. Another method is chemical vapor deposition. I don't know how much you people know about this chemical vapor deposition, but since the further topic is mostly depend on this chemical vapor deposition, I will elaborate it. So typically chemical vapor deposition, there is a heating zone, and there is a vacuum chamber from where we keep our material for the synthesis, as well as the substrate on which we will grow our material. Simultaneously, there will be a gas flow in order to carry these material from one end to another, like basically from the source to our desired substrate part. And in the presence of heat, it will react with each other, and then they will synthesize the desired material. So there are also some advantages or disadvantages depending on the technique. So in case of chemical vapor deposition, as I said, it requires very good good setup, also the higher temperature, and as well as we need to optimize the process depending on the material we are using, and it is not some like universal technique. Depending on the precursor we are using, we require some gas, we don't require some gas. Like these gases sometimes are available, non-availability of these gases, there are different kind of problem. And as well as since it is chemical technique, there is also possibility of chemical impurities. So as I said in last slide, this CVD techniques requires very high temperature, as well as the possibility to uniform synthesis over desired area is difficult. And as you can see in these images, so here is the formation of some molybdenum sulfide using CVD technique. So you can see that some triangular shape, which is basically the monolayers, and with time it can grow to fully substrate. But as you also increase the time, the thickness will also increase. So you need to optimize that that part of the reaction. Then further, I will also introduce some advanced CVD technique, which is also known as the plasma enhanced chemical vapor deposition technique. So this technique basically reduce one limitation of the CVD technique, which is basically the requirement of high temperature for synthesis. So usually the high temperature is also limitation is because you cannot synthesize it on various substrate. You need basically same substrate for like some few substrate in order to synthesize. You cannot use some flexible substrate also, since now world is going towards some flexible variable electronics. So you need to synthesize this material directly top of some flexible substrate. So in plasma CVD, we can do many substrate. We can use many substrate in order to synthesize it. And since I hope you guys may know about the plasma. So basically, plasma is considered to be the fourth phase, and it has some cloud of gases with ions and anions. So typically, if you see the cross section of plasma, at the center there is very high temperature, but at the outer shell it is almost as a room temperature. So it is called as a cold plasma also. And since this plasma CVD machine is based on this cold plasma generation of the gas molecules, it is also considered to be a cold plasma CVD. So typically, if you see the plasma CVD chamber, there is some heater in order to heat your substrate. So we can heat up to our desired temperature. So heat requirement is there because if in presence of plasma can also move depending on the temperature as well as the electric field, since it has ionic nature. So depending on heat also the plasma can move. So we can control the adsorption of plasma on your substrate. So that's why the heating requirement is there. And the plasma is generated using the RF coil, which is basically radio frequency generation of plasma. So there are very different techniques such as inductively coupled plasma, also capacitively coupled plasma. So depending on our required need, we can use different types of plasma generators basically. So here typically I use inductively coupled plasma for synthesis of my Pmdc materials, which I will cover further. So if you see the advantages of these materials, we can do the wafer scale synthesis, basically large scale synthesis, and we can do some low temperature synthesis. Also since there is a chemical synthesis method, it has a chances of higher purity and low contamination as well. But there are other disadvantages such as high maintenance, high cost, since these machines are very rare, some complicated build, and as well as the structure it will produce the material. It also we cannot definitely control it. So there is a lot of optimization is going on for the synthesis using this kind of method. So as I talk, in order to synthesize these 2D materials, there are different ways. So basically in this slide, I am summarizing it. So in case you need to synthesize these Pmdc materials, there are like some metal transformation methods. Then you can oxidize it or sulfurize it. Also the chemical vapor deposition technique which I talked about. Then you can also directly vaporize your powder, and you can make the thin film depending on the thickness you desire. So typically there are these ways which are currently used in order to synthesize this kind of thin film 2D materials for not only TMDCs but other also. So now the properties of this 2D material, I will talk about what are the different phases. As I already talked before, like depending on your band structure, there are some insulating 2D materials, semiconducting as well as conductive materials. So if we electronically and physically see, as the structure changes, this property are changing. So when you synthesize, you also need to consider these things. So what kind of properties we desire in order to synthesize, and we can synthesize accordingly that. So if we consider the 2D Pmdc materials, there are basically a few phases, which also known as a hexagonal phase and tetragonal phase in case of Pmdc materials. So hexagonal phase is considered to be a semiconducting phase of this Pmdc materials, and the tetragonal phase is considered to be the metallic phase. So if you see naturally, 2H phase is very stable for these materials because it is thermally stable, and 1T is metastable or little bit unstable. So depending on how the bonding is there, this structure is defined. So hexagonal, if there is hexagonal arrangement, then hexagonal. If there is tetragonal arrangement, then there is tetragonal structure. So, and as here also you can see, as the thickness changes, the band structure is also changes, which is basically how the nanotechnology is evolved. Because as you restrict the sizes, the quantumness of their band gap is increasing, and you can get some band structure changes, or you can get band gap in many materials. So as I talk in last slide, so 1T structure, if we arrange in this kind of order, you will get 1T, 2H, and 3R. So 1T is basically repetition in only one dimension. That's why there is considered to be 1T. But in case of 2H, the repetition takes place after the second layer. So that's why it is 2H. And in case of rhombohedral 3R, it repetition takes place after the 3 layers. That's why it is considered to be a 3R. And then depending on these phases, we can also, as I said before, the 2H phase is semiconducting phase. So using that band structure, if we can also synthesize the heterostructures of these TMDC materials. So here typically the formation of heterojunction between the band gap of MOS2 and WS2 is shown. So here the band alignment takes place, and eventually the lowering and extending of band gap can take place depending on the arrangement we are doing for the heterojunction formation. So typically here you can see the two kind of heterostructure formation. Here is a vertical heterostructure formation between MOS2 and WS2. So here typically on top of each other, there will be heterojunction formation. So typically here the band structure will show individual property of MOS2 and WS2, and as well as the heterojunction region. And here in plane or lateral heterostructure formation is also takes place. In basically there will be a region with the heterojunction band gap, which will be in between the band gap of two other materials. So depending on this band gap, these materials can be used in many fields such as solar cells, photovoltaics, or photosensors applications. So main thing you need to understand about the van der Waals nature of these 2D materials. So because of this van der Waals forces, we can stack them each other, we can separate from each other easily. And then since this arrangement is same along the other materials, so it is easy to align them on top of each other, because the band structure will also change upon the orientation of top and bottom layer. That's why there is need to be a lattice alignment also. Plus, we can also do some layer by layer stacking by selectively growing, such as from one material to another, then third, or again first material. And depending on our band gap, the number of layers which we are synthesizing, we can also tune the band gap depending on our required application. So this is typically the work we did in our lab. So typically in plasma CVD, we grow these kind of 2D materials. So here we are showing the 4-inch wafer synthesis of these 2D materials. Here the MOS2 or here the WS2 synthesis, which was grown in our lab. And we also published this in other many papers. So typically we take our substrate, we deposit some metal layer. In case of MOS2, we will deposit MO. In case of tungsten, we will deposit tungsten. And then in the plasma chamber, we will sulfurize it using sulfur plasma. And then it will eventually form the MOS2. So as we have found out, the dominant phase in our synthesized material is 1T along with the 2H. So that's why we are calling it as a 1T MOS2, since almost 70 to 80% phase is 1T phase. So in order to after the synthesis, first we use Raman spectroscopy. So as you people may have learned about Raman spectroscopy, so typically we use that technique to firstly confirm the formation of these sulfides. So typically MOS2 and WS2 show this E12G and A12G peaks. So depending on the peak formation, we can also separate the 1T phase as well as the 2H phase. Since there are additional J1, J2, and J3 peaks will be present in 1T phase. So similarly, the Raman technique you can also use to confirm the uniformity of the synthesis process. So even if you use another technique to synthesize, you can use the Raman method to confirm that the whole area is synthesized or not, which we'll also talk further. So here we also synthesize the heterostructure, like vertical heterostructure of this Pmdc materials. And we also initially confirm it using Raman spectroscopy. So now in Raman spectra, as you can see here, the presence of all 4 peaks for WS2 and MOS2 will be there. And typically using Raman, we also did Raman mapping. So I don't know how many people you may know, but using Raman, we can map the some area also. And then using that area, we can map map that image, and we can also calculate the few parameters, such as if we calculate the distance between these 2 peaks, then we will get the knowledge about the how many layer will be present there. So depending on by this calculation, like as I shown here, we can calculate the peak difference, and from the mapping those regions, we will know that the how uniformly our material has synthesized there. So if the peak difference is too much there, then we will see too much variation in the mapping region. But in order to confirm the uniform synthesis, we use this Raman technique to confirmation of this uniformity. Further, you people may also learn about the atomic force microscopy. So this technique can also be useful for the uniform thickness formation of these 2-dimensional materials, not only the TMDC, but other materials also. So along with AFM, there are some other AFM techniques also. For example, Kelvin probe force microscopy is there, or electrical force microscopy will be there. So depending on what kind of property we are measuring, this AFM technique we can use for multiple purposes. So here I'm showing the example of Kelvin probe force microscopy. So Kelvin probe force microscopy is basically used in order to measure the work function of the surface. And you people may not to remember that AFM is basically the surface analyzing tool, not the bulk analyzing tool. So it will basically measure the surface of the sample. And Here you can see the difference between MOS2 and WS2 as the area it scans. You can see the difference in the work function, and this is the topography, or basically the surface mapping of this same region. So topography is showing the thickness measurement, like thickness of this edge region, which synthesized for the in-plane heterostructure using our method. Further, you people may also know about the TM, like transmission electron microscopy. So typically, how you may have seen some different images for other materials, but for 2D materials, this kind of techniques you can use in order to see the cross-sectional region. So typically, how the cross-sectional region takes place is basically you need to cut your sample using some electron beam techniques, which we call the focus ion beam technique, and then we cut our sample, and then in the TM microscope we can see that region. So this is the TM images for WS2 synthesis we reported, reported by our group. So here typically you can see the some 5 to 6 layer formation of this WS2 layers. And then if we also do some top view of these synthesized materials, we can find out some different phases present. For example, like 1T phase or 2S phase region. So depending on the molecular arrangement, you will get the different fringes, different distance between the layers, as well as the so typically 2H and 1T phase. Typically 2H and 1T phase will have a different layer distance. So from that we can easily identify, as well as the molecular arrangement. So another technique you can use also is the Fft calculation. So from Fft also you can easily get the different grain structure. And here is the time study of TM, of how the synthesis takes place in plasma CVD. So typically, as I talked before, we deposit the metal layers. So here you can see there are no any layer formation or anything. But eventually, as you grow or sulfurize these metal layers, the size will increase with the layered formation. So typically, as here you can see, there are some appearance of few layers, or like some amorphous nature we can also talk about, and then it will start to rearrange between them and will form some layered structures. So eventually, after full growth, you can literally see the full layer and full layer formation of these materials. Okay. So further, this along with TM, there is also Eds mapping, which is also mapping for elemental mapping. So we can see the different elements in this Eds mapping. So here, this is the image of in-plane heterostructure formation or lateral hetero junction formation, which was prepared by me. So here you can see the two different regions for MO and W and the sulfurization region. And here also you can see the layered formation. And the second image is about vertical heterostructure formation. So here you can also see there is some brightness difference, like bottom and top. So which is also due to the size of the MO and W atoms. So depending on size, the brightness of the TM can be changed. So if there is high atomic number, it will be more brighter because electron scattering will be higher. So in TM, basically, we measure the scattering image. But depending on what kind of mode we look, we can change the brightness. Like we can also, if we are measuring in the dark field, it will be bright. If we are measuring in the bright field, it will be a dark. So we can arrange that. That's why you need to specifically mention what you are measuring if you ever report this kind of images. So in latter diagram, I'm also showing the mapping of these structures. So this 2D heterojunction formation is also confirmed using some TM mapping images as well as some Raman and AFM. Further, you people also know about the X-ray photoelectron spectroscopy. So how these techniques we can use to confirm the formation of the sulfide, oxide, or other kind of materials. So typically, every element have its characteristic spectra. So here the MO 3D will give some characteristic spectra. In case of tungsten, the 4F will give the characteristic spectra. And depending on the bonding, so in typically XPS, what we look about the electron ejected from the material, and the environment from the electron will eject. It will affect your binding energy of that electron. So if the tungsten is surrounded by sulfur, the environment is different. If tungsten is surrounded by another tungsten, the environment will be different. Since then there will be a big difference between these two electrons emitted from these two different conditions, as well as XPS is typically used to also map the elemental composition. So if we take the area of this curve, then we can and compare with each other, then we can also find the composition, such as what is the ratio between the tungsten and sulfur, or molybdenum and sulfur. And we can also find what is the vacancy of this. Suppose there is some vacancy, for example, oxygen vacancy or sulfur vacancy. We can also easily find out using this XPS technique. So XPS is also useful for detecting the vacancy, and it is easily calculated by taking the area under the curve. And there are some XPS concentration calculation formulas which you can use to find the concentration. Further, the application part of these 2D materials. Next. So as I talked before, so these 2D materials can be useful for enhancing the property of another material. So in case of HBN graphene circuit, so typically if you look at the graphene will have some Dirac band gap, but if the substrate is different, then or not insulating or semiconducting, then the Dirac region will be not found, or that pointed region is not present. It will be merged from top and bottom. So we cannot use some spintronics which can be useful in this kind of devices. So if you put some insulating 2D layer such as HBN, then this direct state of graphene can be easily found. That's why the enhancement of properties can be done using this HBN thing. And another image is about the photovoltaic effect, or basically the solar effect of these 2D materials. So here the two types of MOS2 dope materials are used, and depending on the exposed region, the photovoltaicness of this Pmdc as shown. So as you expose the different part of these heterojunctions, you are getting the different photovoltaic voltages. So this kind of study can be done for this kind of 2D materials and useful. So another application is hydrogen evolution reaction. So typically, many researchers are also working in this field in order to produce the hydrogen from the water, and which can be alternate source as a energy. So typically, it can be also useful for to replace your batteries or fuel or the petrol, diesel in upcoming future. So typically, hydrogen is evolved at the anode or cathode depending on the what kind of process we are doing. So typically in HER process, for the negative voltage, you will get the hydrogen evolution at your electrode, and depending on the conductivity and the conductivity of your material, the hydrogen evolution can be more or less. So typically the platinum is considered to be an ideal material for the base hydrogen evolution, but since platinum abundance is very costly and low in the earth, so people are working in order to find the same performance of platinum, but with other materials. So typically this field is working in that direction. So as you can see, depending on the phases, the hydrogen evolution is taking place more. So in case of 2H, which is semiconducting phase, which basically will result in the low formation of hydrogen. And in 1T, the conductivity is higher due to the metallic phase, will be the case. So typically here the higher performance is considered to be the higher current, which is basically higher number of electron generation, which also reflects the higher hydrogen evolution. So typically from that calculation, you can find out the how much hydrogen you can you are evolving in these materials. And then you can also do some Nick-Visit plot or impedance spectroscopy in order to find the what are the other things which are restricting these materials. And so here the Nick-Visit plot, as your material is showing very better performance, the Nick-Visit plot will show the smaller radius for this semicircle. Further, these two Pmdc materials we can also use for the photosensors or photodetectors. So this is also my work, and we publish in ACS Applied Material Interfaces. So here the prepared heterostructure we use for the enhancement of current generation using light. So typically the dark current we can see here, and in presence of light, the current is enhanced. So typically here is the study of stability of these photodetectors and how much faster switching it can go. So in order to, it can be used for many different applications or time dependent applications also. So typically in our case, we found almost 60 millisecond time between switching on and off for this prepared to 2D Pmdc heterostructure materials. Further, I also use these materials for the photocatalysis. So typically, which is a topic of our today's seminar, is solar energy materials. So basically, the HER, which I talked before, can be enhanced using solar radiation. So which is basically will produce more hydrogen evolving in that processes. So typically it will be the same setup, but with the solar radiation or other radiation also can be used. So typically in presence of light, you can see here the HER performance is highly increasing, and which is also checked using the stability of this material. And also here I am showing the comparison between the different materials. So typically here also you can plot the Nyquist plot or the impedance plot, and you can also find the same relation, which basically confirms the whole story of your materials, like why there is better performance for particular material. So it needs to be check out all the parameters in order to confirm your properties of material. Further, I will also talk about the field effect transistors. As many people know, basically from physics background also, that the transistors are very important components in our electronic industries. So these materials are also useful. Since these materials are semiconducting nature, they can be also useful for the generation of transistors. And typically MOS2 is also known to use in this transistor due to its high on-off ratio. So these materials are very useful in this transistor industry. So now I come to the last section of this presentation, which basically I will talk about the importance of these 2D materials in upcoming technology. So now recently you people may have heard about this Vedanta Foxconn controversy in the news, since our news channels are very detailed about this controversy. So typically what is this Foxconn was gonna do is they will be setting this electronic manufacturing, basically the transistor chip formation units in India. So this kind of next generation transistor formation also used by these 2D materials, because if we look at the semiconductor industry, there are very different components, different materials which can be used. And the goal of the semiconducting industry is to reduce its size for the generation of more transistor per area and all. So typically, as the dimensions are more and more restricting, the usefulness of silicon is like reducing, and people are searching for some alternate materials to compensate the loss of silicon is taking due to the restriction of its dimensions. So that's why many companies are also simultaneously working in these 2D materials. That's why I'm saying that the 2D materials are kind of a next generation materials. So typically here, you can see this is a typical planar field effect transistor device. And if you increase its height, or you can find make it fin kind of structure, it is also considered to be a FinFET, which is covered from the 3 region, the gate is covered. So that's why, like, more the gate area you can cover, it will give the more control on your transistor. So you can make a very good calculations using that transistor, since you can accurately control the on-off-ness of these transistors. And then there is gate all around transistors also. So you can see here, like from bulk, it is also going into 2 dimension. So further, recently IBM also announced 2 nanometer gate all around FET assembly or FET technology. So here you can see the thickness will eventually be lower and lower and lower in case of silicon. Definitely this is not 2 nanometer image is given by the IBM, but this is typically I think this is 10 nanometer or 7 nanometer, which is currently used by many transistor electronic development technology. So here, as you can see, from FinFET to gate all around, and eventually from 2D to 1D materials can be also in the further can be useful for this formation of these transistors. So as I talked before, so the goal of this electronic technology, electronic industry is to develop the more and more transistors in the same area. So as you can see, over the decade, people have done very good research in order to increase the number of transistors in particular area, and eventually they will use other 2D materials for the semiconducting nature. Due to the semiconducting nature in this transistor device calculations. So along with the transistors, this 2D materials is mainly useful for the flexible electronics. So nowadays there are craze about variable devices. Some people are putting it on your elbows, knees, and checking the how you're running, how you're playing, or whatever you're doing. Or people are also using some smart watches and all, like which can also check your heartbeat or whatever things, or like oxygen also. So this kind of devices mostly use this kind of materials because you need very in low amount and restricted use. That's why these 2D materials are used in those fields. So to summarize this topic, as I said, 2D materials are very fascinating and interesting. And these various 2D materials, for example, graphene, HBN, and black forest can be used. Depending on its thickness, bonding, and structure, the properties changes along the materials to materials. And the various methods such as CVD, hydrothermal, as well as the PCVD can be used for the synthesis of these two-dimensional materials. So this synthesized material we can analyze, as I shown, using Raman TM, NAFM, and the analysis needs to be consistent over all the analysis technique in order to confirmation of these materials. Further, depending on what the properties we are looking at, we can use it in various applications such as photovoltaics, HAR, sensors, and transistors. So these 2D materials will be definitely the future. Thank you.
Thank you very much, sir. If any participant in this audience has some query or problem, so that we can answer. Thank you very much, sir. You have thrown light on graphene material, 2D material, its detailed synthesis techniques, Pmdc material, band gap alignment, MOS2, WS2, and so on. This seminar is built with intent of active and interactive session learning. We sincerely hope that the idea and all the effort that you have spent will make it seeds for the work of the future of our students. Thank you very much, sir. Now, we have joined via online mode Dr. Praveen Vartik, sir, ICT Mumbai. On behalf of Nanotechnology College, Mansur, we welcome you, sir.
Yeah, thank you very much, sir. Thanks a lot.
So once again, sir, on behalf of Nanotechnology College, we heartily welcome you, sir, for this today's program. I would like to request Kumavan, sir, to introduce today's speaker, Dr. Praveen Vartik, sir. Thank you, sir.
Good afternoon, sir. I heartily welcome for international one-day seminar on nanoscience, nanotechnology. This is third session. I am briefly introducing our keynote speaker, Dr. Praveen Vartik, sir, Assistant Professor, National Center of Nanoscience and Nanotechnology, University of Mumbai. Dr. Praveen Vartik has obtained his PhD from Naples University, Federico II, Naples, Italy in 2010. Before his PhD, he worked at CSR, National Chemical Laboratory, Pune. He has done postdoc in France. His research area is energy, nanomaterial, thin film, and nano devices. He has published 15 articles and 5 patents filed, 2 books to his credits. Recently, he is writing science articles in Marathi. Just in first session, you have the problem of pronunciation. And to elaborate the knowledge of nanoscience to the people who are having the Marathi language, he is writing Marathi articles in newspapers for the elaboration or awareness of science and nanotechnology to the society, especially our Maharashtra. His research in energy storage, especially fast charging. Daily we have the problem of mobile charging. We want fast charging devices in mobile, and that we are using now. A lightweight, that is handy mobile we require. Lightweight battery and long life batteries. The battery should have the long life. That's why it is very applicable research in nanoscience of Dr. Praveen Walke sir. He is a member of Board of Studies, Dr. Babasaheb Ambedkar, Marathwada University, Aurangabad, Amity University, you know, that is located in Noida, and our university, Saidabad Pune University, Pune, and also the Babasaheb Garwari College, Pune. He is an active member of Board of Studies, means making the syllabus of UG and PG, and also the project director. He is a recipient of Young Scientist Research Grant from DST, Department of Science and Technology, and a good reviewer of Recognition Award 2017 by the Baba Atomic Research Center. Today, third session talk title is High Energy Stored into Hybrid Nanomaterials via Intercalated Pseudo Active Mechanism. I request Dr. Praveen Walke sir, please deliver the today's third session talk. Thank you very much.
Okay, thank you, sir. Thanks for such a nice introduction. I hope I'm audible to all, right?
Yes, sir.
Yeah, is my screen visible?
Yes, sir.
Okay, first of all, let me thank the organizers for giving me an opportunity to be here, and a special thanks to your principal, organizer, as well as Dr. Chaskar for giving me a last hour time to join your conference here. So I'm very delighted to discuss some part of our research activities here related to high energy stored into hybrid nanomaterials via intercalated pseudo-capacitive storage. So before going into the detail about the real presentation, here are some outline of my presentation today. I will initially give some glimpse of the introduction and why this energy storage is important, number one, just for sake of undergrad and postgraduate students. Then we'll see what are the important energy storage techniques available around. I will just scratch details about how the energy storage mechanisms can differ each others, and then we'll just look into how the electrochemical storage differs, like for example batteries and supercapacitor. How can we compare those electrochemical storages? And then we'll see important engineering aspects of various nanomaterials, because engineering nanomaterial will help us to improve our charge storage mechanisms into the various materials. And then later on, I will show you some of the real examples from our laboratory, where we have developed various hybrid nanomaterials and which we use to store the energy, and especially as we seen in the title, that is intercalated pseudo-capacitive storage. And then we will conclude this presentation. First of all, before going into detail about the real this one, we have to just look into what are the global energy scenario, right? So in the natural global energy scenario, there are certain challenges, and that challenges need some certain actions from the society, right? So what are the facts? You can see here on the left side, there are certain facts, and right side, you can see the action needed. So first of all, we know that population growth is the major challenge in front of the society, right? And India and China is contributing too much to these particular facts. But in order to overcome this problem, we need to have some action, like limit of the growth of populations. But that individual cannot help to do this. Probably the government policies will help us to take over this challenge and find out the solution or action needed for that. For example, the China had already taken the decision to have one-child policy, but recently they have scrapped those policies. Probably in India also we may have similar strategy in future. Second important fact was, we have to have increasing energy demand. Just because of the population growth, demand it certainly increased, and that increasing energy demand is a major challenge for us. So how can we fulfill that challenge? So increasing energy demand will fulfill just by increasing the efficiency of whatever the existing energy supplies. Whatever the existing energy supplies are there, just improve the efficiency to fulfill the need. But that is really limited, and that's the reason another fact generated. So what is another fact here is limited reserved energy, right? So we have the limited energy resources available in the market. Though we increase the efficiency, the resources itself are of scarcity, right? So they are limited resources. And how can we overcome this problem is that we need to find out major alternatives or better alternatives and other energy options, other resources we need to explore. And this action is required in this scenario. So there are certainly so many energy sources, resources available around us. We have to just look into it. For example, we have the sunlight, we have the energy, we have the wind, we have the water, and so many things around us. We have to just explore those energy resources and utilize it very properly, right? But while exploring those alternative energy resources, we need to look into another issue, that is environmental degradation. So environmental degradation may happen just by over expectation from the environmental resources. And those resources, if you don't want to do the environmental degradation, in that case, we have to really look into the new clean technology. Clean and green technology is the ultimate solution to protect the environment and at the same time generate or store the more energy or explore the more energy options. So these are the general global scenario around us, and we need to carefully look into those facts as well as action needed. It means we need to have the new and clean technologies to protect the environment and store the energy. So ultimate resources are already available. We have to just increase the efficiency of that and then fulfill the demand of this population. So this is how the scenario of the global energy problems are there. These are the facts and solutions. So what is the energy gap in the world? So we know that half of the world population, right, subsists at agrarian or lower layer of energy access. Half of the world is having excess of the energy access and half of the world is having very less, right? So the population density decreases. So what is the scenario in India? Look at India. Nowadays, India is already decided to have smart cities. And therefore, as the city population growth is increasing, and the smart cities expectation is also increased, we need to have very good sources of energy, and enough energy or energy requirement is very high, not only in the daytime, but also in the night times. Right? You see the lighting of these cities require more and more energy. But at the same time, if you look at the Indian villages, what is the scenario in Indian village? Though at one side we need to have enough energy or more energy to make a smart city, on the other side in villages there is a scarcity or shortage of the electricity. And why this is arising? This is arising just because we don't have enough energy resources available. But the research has given us an ultimate solution that you see here in this figure. There is a solar panel, right? So the daytime, enough sunlight is available in India throughout the country, though in cities as well as in villages. So why can't we store those or convert those sun energy into the electricity? But that can be happen in the daytime, right? Daytime, enough sunlight is available. We can just convert those sunlight into the electricity or energy. And we have to store it into the storage device and utilize in the night times, right? And that's the reason, though you have enough generation of the electricity in the morning time or daytime, you need to have the very highly efficient and high storage capacity devices to store that particular energy so that you can utilize it during the night times or lighting of the cities and so on, right? And therefore, the importance of energy storage materials has improved drastically. And many researchers across the globe, they are looking into the various alternatives, various high storage capacity devices, generation and manufacturing. Another important scenario in case of the energy is like you see the human population expected, for example, since 1950, we have seen roughly there are 64% of the population growth across the globe. At the same time, if you measure the vehicle population, with respect to your human population, you can find out it's exceed up to 195%. And that is much larger than the population growth. It means individual person may have multiple vehicles to him, and therefore the vehicle populations has increased drastically 195%. Okay, so simultaneously the population increase, vehicle population also increase. So vehicle runs a mile or vehicle travels a mile is also increased drastically. That is almost 369%, right? So these 369% miles travel emits a lot of carbon dioxide, carbon monoxide just for burning the fossil fuel, and it can contribute to the global warming, right? So can we avoid this degradation, or can we avoid the pollution so as to control the global warming scenario? And what would be the possible solution to this basic scenario? So you can see here, the city like Mumbai or Pune, they are having huge traffic, and most of the vehicles run on the fossil fuels, and they emit a lot of carbon dioxide, carbon monoxide, and pollution, contribute to the more pollution. So can we convert all those vehicles into the electrical vehicles? Recently, we can see there are so many electric vehicles running on the road, and governments are more curious to tackle this challenge of reducing global pollution just by converting these vehicles. It cannot be completely resolve the issue of the global warming, but at least 4 to 5% of the global warming contribution comes from this fossil fuel burning. So if we can control that 4 to 5% population and 4 to 5% pollution growth, that would be the much contribution to the nature. And here you see these are the different vehicles which has already the e-vehicle and where we use the batteries, right? So those batteries are very important to convert these e-vehicles, convert these pure fossil fuel vehicles into the e-vehicles. So the battery has high energy density, but at the same time you need to have the good power of those batteries. And another thing, while introducing Misa has rightly said that we nowadays looking forward for the fast charging batteries, because just to fill the fuel in the car, we need only 10 minutes, but just to charge our batteries, it needs hours and hours, right? So now the world is so fast and everyone is having a rat race in the market. No one has time to wait until your battery gets charged. And therefore, why can't we convert those batteries into the very fast charging batteries? Can we charge battery within a half an hour or few minutes and then use it for these kind of vehicles? So that would be another important challenge, research community and scientific community is facing. And if we can solve those problems just by developing very smart nanomaterials and enhance the performance of our energy storage devices, these problems will be probably solved, right? Okay, so why to do the material science, right? And what is the importance of the nanotechnology? Usually you see here this is the 2 megawatt solar electricity production plant is here. And this plant is supporting to run this nuclear site, because whatever the energy required to run this nuclear site is, let's say, almost 2 megawatt solar, 2 megawatt energy, and that can be generated from these solar panels. So because you see here, 2 megawatt solar plant requires large land to install those panels, right? So this large land, affordability of the land, now the land cost is going very, very high nowadays, and therefore affording this large land just to place these solar panels is one challenge. Another one is the solar panel size is too big, and as comparative to the size, the efficiency of that is less, and therefore you require the bigger panels and bigger area. Same time you generate the less electricity comparatively, right? So what is the role of the material scientist in this scenario? As this conference is dedicated for the solar energy conversion and its means, so why can't someone use some materials, right? Those will reduce the size of your solar panel, same time increase the efficiency of your solar panel, right? And then requirement of land will reduce. So your land requirement will reduce, the same time energy generation will be higher, right? So if you will have, let's say, very small piece of land over here and put the solar installation plant, and if that will run the nuclear site, would be the better advantages of the current scenario, right? So what is the role of the material scientist? So material scientist's role is like, usually your materials will play a significant role, right? And they will put a huge impact on your societal and economical aspects if you able to fulfill these small size solar panels. So those who can control the material, they will have capacity to control the technology in future, right? So that is the famous quote by the Eiji Kobayashi between the scientists, and that's the reason the material scientists and nanotechnologists are have more responsibilities to control the technology just by engineering those materials. And we will see the engineering aspect for the energy storage properties in our further examples. And here, I just want to emphasize one important quote by Nobel laureate Richard Smelly. He said, the nanotechnology holds the answers to extent there are answers, right? It means, he said that most of our pressing materials needs in various applications will be fulfilled by the nanotechnology. That is the potential. And at the same time, we can see people are expecting too much from the nanotechnology. So nanotechnology expectation is very high. So there are the two important aspects that people are thinking to develop the new materials. So what do you mean by developing the new material? Is it about making the form of the material which was never existed before? So that is my question, right? Why people need to develop? So there are the two important things people are, before developing any kind of the material, people are having some curiosity how that material will behave in the novel form. And another thing is its utility. So how can you utilize that novel properties of the material into the certain applications? So these are the two major aspects when scientists are developing the new materials. So these two aspects are very important, right? Either you have the curiosity or you have the utility in your mind, right? Or people can have mixed feelings, like they will be curious as well as they will think about the utility of that material, right? So there are very novel materials existing, but it may not be exactly in the form of new material. It may be combinations of the material or engineering of the material so that you will get the advanced properties. And then sometimes people can call the similar material as new materials. And here are some important quotes regarding the nanotechnology by the Louis Pasteur. What he said is the rule of infinitely small is infinitely large. Though your material is having very small size, it will play infinitely large role in the development. And this is another important quotes by Richard Fuller and Roman Fuller and Richard Smelly. So this is just an imagination and expectation from the nanomaterials and to fulfill the applications. But those who dream for such applications, they will have one or other day, they will have ability to reach up to that dreams and they can fulfill such dreams, right? Okay. So here, let's move on to what are the various energy storage technologies in the market. Here you see there are the various energy storage things. First of all, we will just have a look on supercapacitor and the battery as an electrochemical charge storage. Though there are the various like pump hydrogen, compressed air, right? And there are various other means of storing the energy, but in this talk, we are only focusing on the electrochemical energy storage. And in that, we are basically interested to know about various batteries and as well as high power supercapacitors and high energy density of the supercapacitors. So how those individual things, like let's say there are the various energy storage, electrochemical energy storage devices available. Here you see the supercapacitor is the one device. Electrochemical supercapacitor or capacitor is there. Why it is called a supercapacitor, that we'll see later on. But that is electrochemical capacitor. Then later on, you will have the batteries and fuel cells. So now you carefully look at this graph. Here at the x-axis, you will have the energy density. Y-axis, you will have the power density, right? So in the energy density scenario, if you look at, you will see the moment you increase the energy density, let's say normal capacitors, which we are using nowadays in the market, that has very low energy density, right? But at the same time, you see the power density of those particular capacitors is quite high, like 10 raised to 4 to 10 raised to 7. The moment you increase the energy density into the supercapacitors or electrochemical capacitors, but this, you see the electrochemical capacitors having broader area than all other three applications, where you have very high energy density aspects. Same time, you have a possibility to increase the power density. And you see this, the linear behavior here. That linear behavior clearly highlights that the moment you increase the energy density, you are compromising the power density of the given device, right? And this is the major problem. So the moment you want to increase the energy density, definitely your power density get compromised, right? But recent trend, if you want to have long life batteries, number one, if you want to have the high power batteries, and if you have the major cyclic stability of the batteries, you need to increase these rather than decreasing power density with energy density. Can we simultaneously increase both the things like your energy density as well as power density and reach up to somewhere here in this region, right? But that is the recent trend in the market, how the energy storage technology is heading towards, right? So here we are looking after, linear increment of the power and energy density, and at the same time, the stability of your batteries or supercapacitors, whatever. So here you see the batteries now. Again, you further increase the energy density, but at the same time, you will compromise the power density, right? So how can we correlate these energy and power densities? That probably we'll see in further slides. And there is another important device, the fuel cell. Fuel cell run car. Recently, CSIR and NCL, in collaboration with one of the industry, had successfully run the completely Indian-made fuel cell-based car, right? But this fuel cell-based car, fuel cell, I can sometimes say fuel cell is nothing but the running cell, right? Where you need to have constant supply of hydrogen and oxygen to your individual electrodes. But in the battery, it is a static cell, right? Battery or supercapacitors, those are the static cell. You have to just once charge and discharge. But here, while charging and discharging, you have to continuously supply this oxygen and hydrogen to the individual electrodes. Okay, let's move forward. How can we compare both these supercapacitors and batteries all together? Usually what happens in the batteries, we know there is a chemical storage happening, and they are having very higher energy densities as compared to your supercapacitors, because whatever the charges stored in the supercapacitor are the surface mechanisms, right? So most of the charges get stored on the surface because of the van der Waals force of attraction on the surface. They get accumulated and form the electric double layer on the surface, and therefore the charge storage happen in the supercapacitors. But similarly, if you look at the batteries, the chemical storage, that is, there is a diffusion of ions or charges inside your electrode, and they get stored within depth inside your material, right? And that's the reason. The moment your charges get stored on the surface, there is a fast possibility to take out those charges because they are weakly bonded to the electric double layer, right? So it can immediately remove from your surface, and therefore the power densities of that particular supercapacitance is very high. It means you can easily take out the ions from that particular device. But in the batteries, when you see the battery, there is reactant diffusion inside the electrode material, and therefore it takes longer time to take out the charges entered or diffused within a material, right? So therefore the power density of the battery is less, right? So this is the basic mechanism. One is a surface mechanism and one is a bulk mechanism. Another important thing here, just a van der Waals force of attraction is there, but in this case, you will have the redox activity that we'll see in the next slide probably. So here you see those batteries, they are having low cyclic life because of the degradation of the electrode, as there is a diffusion happen because of the diffusion, and again, taking out those ions from the electrode material, this electrode degrades, and because of the degradation, the life cycle of that particular or stability of that particular electrode material compromised, and therefore the batteries are having low cyclic life or low stability as compared to the supercapacitor materials. So here are the three important aspects of charge storage mechanisms. As just now I said, there is a EDLC layer formation on the surface, so that you can clearly see here in double layer capacitor figure. So here is your one electrode, and those ions get accumulated. So oppositely charged ions get accumulated. For example, this is the negative electrode. So the positive ions get attracted towards this electrode, and they assemble, or they prepare one layer on the surface of your electrode, right? And that is known as electric double layer formation on this surface. So this is one mechanism, how we can store the charges. And if you revert that particular current directions, or if you apply the load, external load to the device, then it will reverse and you will get an electricity from that particular device. Similarly, if you have having these kind of pseudo capacitive mechanisms, in that mechanisms what happens, where you will have the dominating mechanism is electric double layer. First of all the charges get accumulated on the surface, but simultaneously you will find out there is a certain redox activity happening on that, right? Certain redox activity, certain extent, not more than the EDLC, right? Less than the EDLC, but certain extent of the charge exchange may happen because of the redox activity on your electrode surface. For example, here you see your manganese oxide, and here manganese in the state of 4, right? Oxidations 4 oxidation state will convert into the 3, right? In presence of Na2SO4 electrolyte. So here you have the Na ions. Na ions get interact with this electrode surface, and then it will just take out 1 electron from this Mn and convert into Mn3, right? So this is the slide electron exchange may happen on the surface, and therefore it is known as the pseudo capacitor or pseudo capacitive action. And this is another important scenario where we can store the charges. And third one is intercalated or lithium ion battery type. So here you see, this is one of the electrode, lithium cobalt oxide electrode here, and here is the graphite electrode. So this graphite electrode, you can see it is having a various layers within, and in that layer, while charging, you can see the lithium ion goes systematically within the layer, inside the layer. So systematic intercalation inside the layer. So that is somehow we can call this intercalation, but simultaneously you can see the diffusion into the electrode surface as well, right? So intercalation and diffusion mechanism, at the same time you will have the redox activity with that individual ions, and because of the redox activity, you will have clear oxidation and reduction happening on individual electrodes. So how can we test whether there is a double layer capacitor, whether there is pseudo capacitive action, or whether there is an intercalation or battery type of storage? How can we identify this mechanism is available in the material? So here you can see this is simply the cyclic voltammetry measurements, and many people do the cyclic voltammetry measurement to test what sort of charge storage mechanism is available in the material. Right here is the same thing what we just discussed in the previous case. This is sort of EDLC, electric double layer formation. Right here is sort of pseudo capacitive mechanism. Right, so this B1 is pseudo capacitive because it is a porous electrode and it goes inside and have the electron transfer over here. Right, and in the C, you have the redox pseudo capacitance. So normal pseudo capacitive and redox pseudo capacitive is the two different cases in this case. And you will see here the intercalation, right? Systematic ion occupying in between the layers. So how that can see in the testing of your cyclic voltammetry. Here is the 2 cyclic voltammetric graph. I will give you all 4 separate examples for this CV, but just in this figure, you just try to understand what is the EDLC and the battery type. So this A and B type. So these 2 you can clearly see here. So the moment you will have the cyclic voltammetric graph, which is highly rectangular in nature, in that case, your electric double layer storage or EDLC layer mechanism is highly dominant, right? So the moment you do the cyclic voltammetric measurement, you will realize whether your material is behaving like a supercapacitive electrode or the battery type electrodes. And here you see here rectangular like structure, right? Clear rectangular, and which means that EDLC nature is dominated in your material. But at the same time, if you look at this figure F, so in the series you will have distinct 2 peaks, right? So what these distinct 2 peaks do is, one is oxidation and one is reduction peak, right? So that oxidation and reduction peak will clearly give you the indication that dominance of the redox activity within that particular material. And then you can say this material is nothing but battery type of the charge storage material, right? Same thing we can easily look into the charging and discharging, galvanometric, charge discharge mechanism, if you look at. But in case of nano and bulk, there is very marginal distance, very small distance between, and it's very difficult to identify at a nano scale what sort of phenomenon is there. In the bulk, we can very easily see in the bulk case that there is, you see here in the bulk, that CD, cyclic charge discharge process. So galvanometric charge discharge process you see here. The potential from 1, it is reducing, right? So with respect to time, the capacity will reduce, right? But at the same time, you see here, in case of the battery, there is a little small hump, right? Here, that is a clear-cut hump in the bulk case. So in the bulk case, if you see there is a deviation from the linear behavior, right? linearly, if you go to EDLC nature, it is a linear. If you go to the battery nature, it is having various hump, and you will have the various slopes, right? So this sort of hump will clearly indicates you the battery as well as this one. But the moment you compare both in nanoscale, so what happened? In the nanoscale, you see here, this is the 50 nanometer. So 50 nanometer and bulk is behaving similar, almost similar linear nature. So it's very difficult for you to identify from this galvanometric charge discharge whether your electrode is behaving like a EDLC or whether it is behaving like at nano. You see here at 6 nanometer, that is also looks like a quasi-linear. So this is very difficult to identify, and therefore in nanomaterials case, only we can have the good metrics to measure this is like your CV measurements, right? And also we can have the various charge storage mechanisms, understandings, and I will show you some of the examples how people can identify whether there is intercalation mechanism or redox activity from various measurements of those particular devices. Here is another important thing. This is a comprehensive table where we can easily understand behavior of your material and its charge storage mechanisms. So as we already discussed here, the EDLC, clear rectangular, and we see here bulk, and this is the charging or discharging profile. For example, you see the discharge is here linear in the bulk and this nano case as well. But if you go to there are the pseudo capacitor arises because of the two various phenomena. One is the surface redox activity and another is due to the intercalations. So intercalated pseudo capacitor is very close to your battery behavior, right? But the surface redox pseudo capacitor is very close to EDLC behavior. And this pseudo capacitor is the bridging between the EDLC and the battery nature, right? And that's the reason the pseudo capacitive materials are playing significant role either in supercapacitor or in batteries, or they will have the mixed behavior of the battery as well as supercapacitors. So therefore, the pseudo capacitor or intercalated pseudo capacitor is very famous, and a lot of people are working on these materials to enhance the energy storage capacities and having both properties of capacitor, some properties of the supercapacitor and some properties of the batteries, right? And therefore, this is very famous part, and we will see the examples exactly related to the pseudocapacitor or intercalated pseudocapacitive storage materials. So the surface redox pseudocapacitive material, you can clearly see there is a little deviation from the exact rectangles in the CV, but you will find out the discharge profile will be the same as that of your electric double layer, right? The moment you go into the intercalated pseudocapacitance, you will find out there is a big tail here, right? So though there is a deviation, further more deviation than what exactly rectangular form is having, but you will have further little deviation of your rectangular face, but at the same time, it will increase the tail. And this tail is a great indication that your material is having intercalation, right? And the deviation from rectangular will give you the pseudocapacitive behavior. So intercalated pseudocapacitive can be easily seen by this kind of the CV performances. And same time, you can see there is a hump generated here in the discharge profile, right? There are the two various slopes here in the discharge profile, but nanoscale, you will not see any difference in all these three cases in the discharge profile. Discharge profile remains the similar, right? But the only thing you can see this cyclic voltammetry profile. And in battery case, you can see there is a clear indication of oxidation and reduction peaks. And this oxidation reduction peaks, and this is clearly humps here, and there are at least three different slopes in the bulk case, but in nano case, again, you see it is a linear. So this discharge profile will not give you the exact and clear-cut idea about what sort of the storage mechanism is there, or except these CV mechanisms. So in these mechanisms, what happens is, you see here in electric double layer, in surface redox and intercalated, you will not find there is any change in phase of your material. But the moment you go to the battery type of the materials, you will say there is a phase changes in your original electrode materials, right? So this is an indication that how you can differ the battery from all other characterizations. Let's have a look on ion adsorption. Here you will find out as there is a surface activities, the reversibility in your ion adsorption you can easily see. But in case of the pseudocapacitor, especially the surface redox pseudocapacitors, though there is reversible ion adsorption, but it will continuously change your oxidation states. So oxidation state changing may happen during that. In case of intercalated, you will have, there is intercalation or slowly accessing the space within your layers by the ions, and simultaneously it changes the oxidation states. So simultaneous reactions will happen in the intercalation. Here there is a change in oxidation state as well, and here this cell will represent you the intercalation part, right? But in battery, you will have either intercalation or diffusion in your material and rapidly change in the oxidation states. That's the reason you will have the distinct peaks at the oxidation and redox sites. So if you look at into the kinetics of all these different types of the mechanisms, you will see that this I is nothing but your current, right? So the current behavior of your electrode material, and this nu is nothing but the scan rate. How fast you are scanning your potential from, let's say, range within a 0 to 1, for example. If you are applying the potential 0 to 1, how fast or how rapidly you are changing the scan rate of that. So this scan rate and this generated current has a certain relationship with them. So what is the relationship in case of, let's say, pseudo capacitive and electric double layer capacitive? It is a linearly proportional to each other, right? So the linearity, if you increase the scan rate, definitely you will find out there is linear change in your current values. But the moment you come into the battery, you can see that this current generation is directly proportional to square root of this scan rate, right? So scan rate nu raised to half or 0.5. And this value, let's say, for example, whether nu raised to 0.5 or nu raised to 1, it decides whether your mechanism is surface or whether your mechanism is bulk mechanism, right? So the moment this parameter comes to that, we can call V raised to B. B value, if it is 0.5, it is a battery, and if B value is 1, it is a supercapacitive mechanisms. So in this type, which are the materials are favorable for certain types? So in electric double layer, you see usually the carbon or activated carbon material are more famous. Porous carbon materials are fulfilling the demands of this electric double layer. The moment you go to the transition metal chemistry or transition metal oxide materials, you will find out, and there should be certain Brisnite structure of MnO2 and some other structures, layered structures of various oxides will fulfill the demand of surface redox pseudo-capacitive mechanisms. Similarly, the transition metal chemistry, which has having the large channel structures, for example, you see here the niobium pentoxide, right? So this niobium pentoxide, you see here, there are the different tunnels or channels are there. And these channels will help us to have the intercalation, because a lot of the ions are going and accessing those channels. And the moment they access those channels, there is a tail formation, right? And that's the reason these particular channel-like structures are highly favorable for intercalated pseudo-capacitive mechanisms. Further, we can see the high theoretical capacity of various oxides. Here you see Li FePO4 is very popular battery material, battery electrode material. And that electrode material will certainly have the fast redox activity. And at the same time, you have the various channels and diffusion channels to that material electrode surface. And that will fulfill the demand of the battery materials, right? So this is how the background of various charge storage mechanisms are there. But what is the trend of research in this particular scenario? As I said before, there is a requirement of having balance between the supercapacitive properties and battery properties, so that we will have the very efficient energy storage device with us if we have mixing both the properties together. So what is the recent trend in the science is people trying to develop the material which is having energy density equal to the battery, because we know that energy density of battery is very high. But at the same time, you look at the power density and cyclic life of the supercapacitor. So supercapacitor have high power density, same time high cyclic life. So can we have both properties together, coexisting? For example, high energy density, high power density, same time cyclic life, right? So if this situation will occur, then we will have a very high energy density or very high efficient energy storage material, right? So what needs to be done in this case is that we need to have a proper evaluation of the new material, and we need to know the charge storage mechanism of that material to facilitate the progress into certain field of energy storage materials. So the recent trend is either increase power density of the battery or increase energy density of the supercapacitor, right? So this is the standard trend in the market to fulfill the demand of the energy. Okay, so let's have a look on what are the engineering aspects or what are the various strategies people are using to engineer existing nanoscale materials. Let's say, for example, this is a biochar material. You just burn anything, or you will get the biochar, right? So that biochar is nothing but you can call it as a carbon black or so. So that is very favorable material and existing material for this battery technology or any sort of energy storage technologies. So what we can do is we can engineer those particular materials and we can tune their respective property just by doing a small engineering of that particular biochar material. And we'll see how these particular properties are tuned. Okay, so the moment you take a biochar, let's say, do the post-synthesis modification here. These are the various strategies of the post modifications. First, you do the activation. So activation, it means you have to just heat it into the KOH or some of the solvent, just heat that carbon material, and you can attach certain groups to that, and it will convert into the conducting material. And at the same time, you heat it in presence of that particular KOH, and you will have the activation of that particular material, and that will definitely tune the property, that is specific surface area. And more porosity will generate it inside this particular biochar. You see here, there is a porosity generated within your carbon material, right? And the moment you introduce the porosity, the specific surface area of that particular material increase drastically, right? And the moment, what is the requirement of our particular electrode material is that we need to have the good surface area of that material. Okay, if your surface area is large, then more sites will be available to absorb their ions, right? And therefore, the EDLC layer formation will be higher. More ions will get accommodated on the larger surface area. And that's the reason we require the more specific area, and we need a higher porosity. Important another thing is your electrical conductivity. You need to have the good electrical conductivity of your electrode material. And how can someone tune that particular electrical conductivity? So just by doping your material, let's say, for example, you have one material, and if you dope various metals or you functionalize certain metals to your material, then definitely you will see the electrical conductivity get tuned. And second one is, because of that functionalization or presence of external atoms, those will help you to have redox active sites, right? And therefore your surface redox reaction will enhance because of the dopants as well as functional atoms. And so these two properties directly get tuned or directly get modified just by doping and surface functionalization of the given material. So we'll see some of the examples of these particular surface functionalization or doping in next slides. So third important strategy is like, you can load your metal oxides and hydroxides on that particular carbon material. So by loading those metal oxides or hydroxides, what it happens is your mechanical strength and rigidity of that particular electrode material will increase, right? And at the same time, because of these metal oxide sites are available or hydroxide sites are available for redox activity, surface redox reaction will increase. And this single strategy will definitely help you to increase the mechanical property, so as your stability or cyclic stability will increase. And that is the good advantage, because we are looking for the highly stable batteries as well, right? And surface redox reactions increase, it means your energy density will also increase. So this is another important strategy. And recombination of the functional nanomaterials. So you can just recombine the various functional nanomaterials all together and form a hybrid material. So that hybrid material will also help us to increase the mechanical property of the surface redox activity. So these are just 4 strategies which I have shown you here, which are the very simple and can be easily executed in various college level or even in a small organizations as well. So these are the very basic engineering aspects. If you want to have very good layered materials, then combinations of various layers, then heterostructures and so on, there are some more other engineering aspects are also available. And those who have the good facilities with them, they can implement those engineering strategies while developing the materials. And certainly these 4 properties have to be tuned in a proper way so that our requirement of the high energy storage will be fulfilled, right? Okay, let's look at this one of the good example of the decoration of platinum on CNO. This CNO name has been given to this carbon right? Here you see this is the image. And this image, in this image, what you can see is, just a moment. So in this image, what you can see, this is sort of carbon nanoparticle around 50 nanometer, right? And in this, you can clearly see here, there are these small layers here, right? So what are those small lines indicates? Those small lines indicates that there are the graphitic layers, right? So number of graphitic layers assembled all together, same like an onion. Onion has various petals around it, right? So what happens is that each line here we consider as a one petal, right? So various petals come together and form a ball-like structure, and that is known as a onion-like structure. So that's the reason we give the beautiful name to this material is carbon nano onion, and it is made up of the carbon material as well, right? So what is the strategy we have done? Just now we see that there is a functionalization or decoration of various metal particles into your carbon material, how it behaves or how these tune the charge storage properties of that particular material. Here you see this is the SEM image, right? And this is the TM image. So in the SEM image, you see almost similar nanoparticle size of carbon is there. So carbon onion size. And here is the single carbon onion, which can clearly highlight various petals within it. And here in this figure, you can see there is a decoration. These black dots you can see clearly here on these particular carbon dots. There are the black spots, right? So those black spots are nothing but our platinum nanoparticles. So these platinum nanoparticles are having size from 2 to 5 nanometers. And this total size of this particular carbon particle is 50 nanometers. So on the 50 nanometers, if you have 2 to 5 nanometer multiple atoms decorated on this, how it will behave, how they can, that can change the energy storage properties or charge storage properties of that particular material. And here you can schematically see, this is just a diagram for sake of simplicity. Here, there are the different layers of graphite. And here you see, these are the blue dots on this particular ball surface is nothing but a platinum nanoparticle. So here, this is the Raman spectra, which can clearly tell us about after the platinum decoration, the defect band is increased, and therefore ID by Ig ratio here is decreased. And here ID by Ig ratio is high, so graphitization is quite higher in normal CNO case. Defects are comparatively lower than platinum decorated. So the moment you decorate the platinum, the defect level increase, and therefore ID by Ig ratio is also reduced. Okay, so that is just an understanding about the purity and quality of that carbon materials by using these Raman spectra. Now, as we have seen in the previous cases, that in the CV measurements, right? So cyclic voltammetry measurements, here you see the current density versus potential. And this line here will show you this normal CNO, right? Without any functionalization and decoration on it. But here, this blue curve, you can clearly see that platinum decorated CNO. So now, how can we evaluate? And this particular reaction were done in 0.1 molar Na2SO4 solution, and with the scan rate of 100 millivolt per second. So you see here, area under this particular curve. When you do the calculation of the capacitance by using this cyclic voltammetry, you will consider the area, right? So this area plays a significant role in your capacitance. And the moment you increase the area, ultimately your capacitance value increases because the condition of measuring CV in both the cases were similar. And you see here, this area under the curve is very small. The moment, only in case of the CNO, bare CNO material. The moment you decorate the platinum, you will see the area is opened up drastically, right? And these peaks are shifted towards higher and lower side, depending on which range you are measuring, either in positive window or negative window. It will shifting to higher current density and further higher current density at the negative potential. So this area has increased a lot. What it suggests, it clearly indicates that the capacitance value has drastically improved the moment you decorate the platinum on your carbon. Right? Here in this figure, you can clearly see the current density versus potential. And the moment you see the scan rate, the moment you increase the scan rate while measuring this cyclic voltammetry, with increasing the scan rate, you can clearly see it is opening up the curve, right? Area under the curve is increasing systematically. It means the increasing this particular scan rate value, your storage capacity is increasing drastically. And in case of platinum, you can see there is systematic increase in this particular area under the curve also with respect to similar trend. But the only thing is you can find out there is a shift of these values towards either positive or negative side, depending on which area or which sort of range you are measuring, potential range you are measuring, right? And here in this charge discharge profile, right? Galvanometric charge discharge profile is very beautiful. This you can clearly see that the moment you have only CNO, the discharge is very fast. Charging is very small and discharging is also very small, right? But the moment you decorate the platinum on that, you can see this is increasing, right? So the charging time is also increasing and the discharging time is also increasing. It means what? It means if there is a large charge stored in your material, it requires longer time to discharge. And if there is a large capacity to store the charge, it will require more time to charge, right? So the charging time and discharging time increase will clearly indicates us that there is an enhancement of the charge storage the moment you decorate the platinum on it. Now, just try to understand, just by decorating what happens and what sort of property is exactly tuned so that, this charge storage performance has been increased, right? So let's have a look here. First of all, let's look at the stability part first. After functionalization, how stability get affected, and then we will go to electrical conductivity part of this particular material. So here you see, this is the charge and discharge, So there are a number of cycles here, right? So every line going up is charging and coming down is the discharge, right? So there are more than 10, 15 cycles you can see here. So this one will show you this bare CNO, and this one will show you the platinum decorated CNO. So now you can clearly see here at the top, right? So charging and discharging, the recovery here is not a consistent, right? After every cycle, you won't see the consistent recovery, either discharging or charging. But the moment you decorate platinum, you see the stability here. So the charging, discharging gets stable, right? So it means what? It means that the performance stability will increase the moment you have the platinum decorated on the CNO material, right? So this is what can be clearly seen here from these cyclic measurements. Let's have a look on the specific capacitance value with respect to number of cycles. So the moment you do the 2000 cycles of this similar trend, we have found that the specific capacity of this particular only CNO material is around 60 to 70 farad per gram. But the moment you decorate the platinum on it, we can see it's increased to 350 farad per gram. It means it is almost 350 divided by 50. You can calculate how many times, more than three times enhancement in this particular charge storage or capacity in this material is happened just by decorating. So what exactly happened in your material after decorating the platinum on that? So here, this is the impedance spectra, right? Impedance spectra of CNO and impedance spectra of platinum decorated CNO. In this spectra, you can clearly see this spectra is quite big, right? And this is reduced drastically. What did it suggest? It suggests that charge transfer resistance of that particular electrode is drastically changed. So resistance, charge transfer resistance decrease, what it means? It means the conductivity of your particular material has increased. Increase in conductivity is the major cause of having good performance of these charge storage properties, right? Anyone have any questions so far? Because I can see some voice was there in between. Okay, if no questions so far, I hope that I am audible to all properly. Okay, so let's move forward. Here, this is just an Dft calculations. What we assume here is that this is the C60 bulb, right? So hexagonal nature of that carbon arranged all together in hexagonal nature, and it has formed as a full array material.
Please keep silence. The program of Valediction Function for Fft one-day webinar will begin with a few moments. Please be seated and be silent. Thank you so much.
Yes, may I continue further? Am I audible to all?
Hello, sir.
हाँ.
हाँ, sir, you are audible.
आवाज येते ना?
Yes, sir. Yes, sir.
हाँ, ठीक है. So let's have a look on this simple strategy here. We have just considered the C60 bulb, right, which has decorated by the 4 platinum atoms altogether. So the moment this is just Dft calculations. Yes.
Sir, am I audible?
Yeah.
Sir, we have time constraints, so we have 5 more minutes. So I would like to request you to wind up your session.
Oh, is it okay? Then let me go to one more example and then I will finish it. Okay.
Okay, sir. Okay, thank you so much.
Yeah. Okay, fine. So let's have a look here. You know, this decoration, how that decoration will change the Fermi energy of that particular material. And here at 0, you see the Fermi energy or density of states. Right? At that 0 level, we can see the density of states is increased, and that's the reason you can easily understand why this conductivity has been increased. Okay, so this is one. Let me go to another example. I will skip this example just because of the time constraint. I will skip this example and I will go one of the beautiful example over here. So this material, you see here, this is the sort of hybrid material which has been developed. And what is the material exactly? You see here, this CNO, what we have seen just before, that CNO we have taken and grown these particular MnO2 sheets on that particular CNO material. CNO is used as a support, and on that support, we have grown these sheets, right? MnO2 sheets, and it will looks like a marigold-like flower, right? Total image. Here you see the SEM image of that particular material. In that SEM image, you can see those balls, very nice balls like a marigold flower here. And if you zoom it a little bit, you see the clear petals of the films. And this is the TM image. In that TM image, you can see those petals as, you know, just by sonication, they have fallen down. And we can, in this image, you can clearly see inside this black dot is nothing but your CNO. And out of that, you see here, there are the small curtain-like shapes. Curtains, those are nothing but your sheets, right? And those sheets are assembled into multiple layers. You see here, if you do have very high resolution image, you can clearly see here that there are 7 to 8 layers assembled all together. And these 7 to 8 layers are highly favorable for the ion intercalation within those layers. So those ions will go inside the layers. They will have the adsorption on the surface, but at the same time, they will try to intercalate into these particular layers. And therefore, we call it as an intercalated pseudo-capacitive storage. Here are the 2 different mechanisms of this material, hybrid material will form. One is redox activity, pseudo-capacitive redox activity, as I shown from Mn4 to Mn3 conversion, and same time accessibility of that particular layers by the ions. Okay, here you can see how that charge storage performance has increased, and up to 83% we have observed the EDLC behavior, and rest is nothing but the pseudo-capacitive behavior of this material. Okay, and here you see this is how the conductivity is increased with respect to temperature. We have done the temperature dependent measurements, and we can find out the enhancement with respect to increasing temperature. The capacitance value is increased, but at the same time, you have to compromise your stability, right? And this is the proper flexible device, which has been composed of using these nano sheets, right? And RGO. So here, this is the assembly of your device. We can see the reduced graphene of state as well as delta MnO2. And you can see this device is sustained up to 1.6 volt. So the voltage is very high. The moment you increase the operating voltage, you can increase the energy density of this device, right? And this is the increment, and this is the result of that particular material as compared to the existing material. And we can find beautiful material development by just using the CNO as well as MnO2 sheets altogether. And it has up to 10,000 cycles. And I will skip this example. I will go to the direct working device model. You can, for further reading, you can use the chapter number 12, how to do the 2-dimensional materials engineering. This is another example of the tunnel material, which is there, right? So I just skip this because already I have mentioned all of the basic about how these things are changing with respect to bending, you know, with respect to bending angle, the capacity is remaining same. It means it is highly compatible for bendability. right? And let's have a look on the working devices which we developed in our laboratory. Here you see there are two devices which connected all together, right? Each device is made up of 1 milligram of the material. So only 2 milligram of the material is there. We are just charging it at 3 volt for, let's say, 30 seconds or so, right? So you can see here the 30 seconds charging, and this LED is glowed, and that LED will run more than, let's say, 3 minutes or so. So that is a very beautiful example of the material. Another important application here you can see is, same two devices attached in a series, and this external fan which requires 1 volt of the energy, and we have charged this particular device, let's say, for 30 seconds. Here only 60 seconds has been used, and then this fan will be run more than a minute or so. So that means this small amount of the material has stored huge energy so that it can take a load of 1 volt. So you can imagine, so less amount of the material having a capacitor stored a huge amount of energy. So this is what I tried to show from this particular video. And with this, I would like to go to the last part. This is the new materials has been developed. You can go and read our recent carbon. Okay, so this is different Internet of Things applications are there. So I will not go into detail about this at this moment because of the time constraint. And those who are interested to read about the future of this, these are some media attractions which we have already reported in various journals. These are the various nanomaterials developed in our laboratory so far. These are some other materials also developed in the labs. So I don't have time to show this magic equipment. These are the various Nobel laureate visits to our laboratories. And this is my research group, which I would like to acknowledge over here. And with this, I would like to thank all the, thanks all listeners, students, and organizers. If you have any quick questions, I would like to respond to you.
The session is open for question and answer session. Anybody has questions? Okay, thank you very much, sir, for your interesting and stimulating discussion.
Yeah, thank you. Thanks a lot.
Meaning knowledge is the first step towards the wisdom, but sharing it with others is the first step towards humanity. For all the knowledge that you have shared with us will really so valuable, and it will inspire us to work for the budding management. Thank you very much, sir. So meanwhile, we have interrupted you, so sorry for inconvenience to you. Praveen, sir?
That's fine. Thank you very much. Thanks a lot.
Sorry for...
Yeah, it's my pleasure, yeah.
Thank you very much, sir.
Yeah.
Now move on towards, we are moving towards the valedictory function, and now I would like to request Dr. Kare, sir, to address the gap group of this valedictory function. Thank you, sir.
बऱ्यापैकी वेळ झालेला आहे याची मला कल्पना आहे पण सकाळी 9:30 वाजल्यापासून आपण एनर्जी कन्झर्वेशन अँड कन्व्हर्जनचे लेक्चर ऐकतोय त्यामुळे बऱ्यापैकी तुमच्याकडे एनर्जी अजून आहे मला माहित आहे जरी संपत आली असली तरी एनर्जीचा फॉर्म असा असतो वन फॉर्म कन्वर्ट टू अनदर फॉर्म त्यामुळे तुम्ही आता ती एक शेवटच्या 15 मिनिटाकरता तुम्ही स्टोअर करून ठेवा मी कंबाइंड गोष्टी एकत्र करतो शेवटच्या सेशनमध्ये डॉक्टर प्रवीण वाळके सरांनी अत्यंत चांगल्या पद्धतीने आपल्यासाठी व्याख्यान दिलं लेक्चर दिलं त्याबद्दल मी आपल्या त्या सगळं ऑर्गनायझिंग कमिटीच्या वतीनं आणि महाविद्यालयाच्या वतीनं त्याचं मनापासून आभार व्यक्त करतो आणि त्याच पद्धतीनं फ्रॉम मॉर्निंग you have heard a 3-4 sessions. Inaugural session is under the control of President of College, Dr. K.G. Kanade sir, where you have to listen Dr. Dinesh Ambalkar sir, also the Dr. K. Kalyan Sundaram sir, very well on the solar energy and conservation materials and the reforms means They have delivered very nice lectures. Then after the second session, a very nice lecture was delivered by Dr. Chaitanya Kanadi sir. Also on online session, right now, Dr. Praveen Kwalke has been delivered a very nice lecture to all for on the topics solar energy, conversions, and materials. Different kind of materials, different kind of the energy sources. I think this one-day seminar is very informative and knowledgeable to you all. All the dignitaries on the dais, coordinator of, I take this opportunity collectively to all here to express as a what we call a presidential talk as well as the vote of thanks at the simultaneously. I express here vote of thanks of the organizing committee, particularly principal of the college, Dr. K.G. Karnad sir, then vice principal of the college, Dr. Bolbar sir, then all the organizing committee coordinator, S.T. Shinde sir, all departmental heads of the science faculties, then the all faculties of the science, all students actually participated from the various colleges. Particularly from Narayana College, the staff has been joined to this session and this conference. So I warmly, extremely thanks to all that faculty of Narayana College as well as students. Also, all anchoring members of the conference, I thank them. Then Mr. Karali is also here. He has been made provision of the online lectures and Zoom meetings. So on behalf of all organizing committee, I directly, indirectly involved all faculty members and students. Once again, thank you all. And there is one more suggestion that you have given, you will get very shortly a feedback form. You have to, every participant should fill that feedback form. Then after you are eligible to obtain your participant certificate. You will get a participation certificate online mode only after your submission of feedback form. And there is one more also request you all of you are made arrangement of lunch in the Aniket Hall. So kindly you all go there and take the. Thank you.